Hi, this is your TA, Asif. Today we are going to talk about Lab 5, which is RC sinusoidal oscillators. Now, before we talk about the oscillator, let's get a very brief idea about the crystal oscillators, which has been around for a long time, and we have heard the name like crystal oscillator. So the crystal oscillators, they are pretty good in some tasks, but they also fail in to perform some duties. For example, you can have a very precise output, and the effect that we know, like this called the piezoelectric effect, which is like you can get the charge. I mean, you can create a mechanical vibration from the charge or vice versa. But anyway, the problem is the crystal oscillator is very simple, yet they are untunable. They cannot be tuned. Once you have built one, that's like the single frequency it will do. It will be delivering its entire life. So that kind of limits your application. So in this lab, we're going to learn how to create an AC signal from a DC source. So if we think the other way, we can get the DC from the AC in a very easy way. Like you can use two diodes and you get DC. You can use the capacitor to smooth out the signal. But the getting AC from DC is a lot more trickier. And we are going to talk about the concept of marginal instability, like it's not stable or unstable. It's like somewhere in between. And there is also a simple analogy, like a simple pendulum. Let me go through this concept real quick. Like if you want a pendulum to oscillate for a long time or for eternity, you have to put some energy into it, right? But you have to put it in the right moment. Like when it's coming back to you, then you give a push. But when it's like on the way, it's traveling, if you push the other way, it's not going to help it to oscillate. It's just going to stop the pendulum anyway. So the oscillator is a marginally unstable amplifier with a filter stage. So that means when we talk about an oscillator, it is a marginally unstable amplifier with a filter stage. So there are few stuff that we need to concentrate on. First thing is like marginally unstable. Then we have an amplifier. Then we have a filter stage. So we'll see what it is. It's pretty wordy, like it has a lot of things in it, but in reality it's simple to understand. Excuse me. And for a sustained oscillation, what we need is we have the system gain. So if you sum all the system gain, and it should be equal to system loss, so that you don't lose any energy and you don't add up anything. So it just goes on. It doesn't run away or it doesn't die off. So it just goes on and on at a predefined pace. So the last point is you have to put the energy, you have to add the energy at the right moment to help the oscillation to go on. Like it's just like the pendulum that we mentioned. And it also relates to the sum of the system loop phase angle. That means like that actually defines the right moment. Now there is a criteria which is very simple. The criteria is we have seen this kind of diagram, right? Like you have some input and you have some system properties, like it is then you get the output, and from there you have the feedback loop. So it's pretty common thing, and the relation between the input and the output is given by this. We all know that. So the criteria that defines this circuit to oscillate is this. Your angle of this and this should be 180 degrees, and the value, the amplitude of this term and this term should be 1. So these are just two conditions. You just have to satisfy these two. Now the reason is you have a negative sign in the summer. When you sum up this input and the feedback, you have a minus sign. So technically you have to get system gain equal to 1, and your net system phase shift is 360 degrees. So you get this 180 degrees and when you have the minus sign you actually get another 180 degrees, so that's 360 degrees. So together this is called the Barkhausen criteria, and this is what it states, like you have to get a system gain of 1 phase shift of 360 degrees. Very simple requirements. Now this is something that actually satisfies our requirement. This is the RC phase shift network. It gives you the required phase shift, and here is the inverting op amp creates the required amplification. So here we actually have both, like as I said, I need to create some phase shift and an amplification. So it's an oscillator, and the analysis is really complicated. It's, trust me, because if you look at the expression you can see it is not very simple, but if you are willing to see in detail you can look at the lab manual, it has all the derivation. But there are few assumptions. For example, you are not loading the next stage. For example, if you have something here and the next stage draws a lot of current, that's going to load the previous stage. We are not going to do that. We are assuming that everything stays fine, there is no severe loading. So you have to think about that when you pick the C and R. Anyway, the frequency response function is this, and this is 5.13 from the lab manual. So we are not going in detail like how this thing came here, but we are just going to use the concept. Like we are going to apply the Barkhausen criteria here, which is really simple, surprisingly simple. So we say the phase angle is this. How is this? Like if you look at these two terms, so we know it should be the inverse tangent of this and this. So that's it. Like this is the term and this is the term. So if we go to the next page, you see those terms. So this is just the angle, like the complex number, you have the inverse tangent of both the real part and the imaginary part. Now we say the angle should be equal to 180 degrees. So tangent of 180 degrees is 0. So you just equate this thing to 0. Then you just get the frequency. Okay. So that's it. That's what we needed. Like through all those analyses and things, we actually need just this one single equation. Your frequency is 1 over twice RC pi square root of 6. So you got something out of it. And then there is the gain term. Like this is the expression from the last slide. So if you go for the magnitude and if you substitute the value of f that we found here, so we just solved everything and we got this. So you don't have to solve it by yourself, it's already done. So as you can see, it's 1 over 29. That means like you are losing about like 28th of your power out of 29. So that means you have to gain 29 times. All right. So from this circuit, your frequency is defined by this, and you lose, like you just have 1 over 29 of your input. So you have to put something which amplifies it by 29 times, and then you get 1. So we are kind of like we are in pretty good shape. We know how we can tune the frequency, and we just need 29 times gain. Now, how do we do the design? It's very simple. From the equation 515, which was this equation which dictated the frequency, find R and C. So just choose any C and then solve for the R. It's just a single unknown here, the R. And we pick the C because we have limited values of the capacitor. We don't get capacitor in any value. From the inverting op amp's gain equation, find the remaining two resistors. That means you have to use the inverting amplifier, and there you have to get the gain of 29. Like as we did before, we did the inverting amplifier before, and we know how we can tune the gain, right? like if you have the equation R2 over R1, then you can pick the gain. And resistors should be large, since we have analyzed the circuit assuming the output loading is minimal. That's what I mentioned before. And these are just two common sense. Like if we say large resistance, that means small load. If we say small resistance, that's large load. All right. So now here is something like how the oscillation starts up. Generally, there is some thermal noise like everywhere. Unless you go to absolute 0 Kelvin, there is thermal noise everywhere. So those noise will start up your circuit. They will start creating voltages at any different frequencies, all the frequencies. But since you have the filtering system, like the RC filter here, they will pick up a frequency. So the other frequencies will die off from the thermal noise. It goes like this. You have the thermal noise, everything is generated, only one frequency survives, that goes to the amplifier, that gets amplified and goes on and on and on. So that's how it works. So anyway, this is just for your information. That's how the thermal noise works. That's something nanovolts per hertz, and there are many things we have to think about, like if you consider the one-sided power spectral density, but we don't have to care because in real life you get the thermal noise without any effort. But in your simulation there is a problem, like there is no thermal noise actually waiting for you there. So what you can do is you can add some initial noise source. The commonly used technique is to define an initial voltage across one of the capacitors. Like you can define that this resistance had 1 volt, for example. So if this resistance had 1 volt this capacitor had 1 volt as a starting point, then it will just go on and it will just start up the entire circuit. All right. So here is the simulation. Like you have to get something that gives you 29 terms of gain, and this is the required specification. I want a frequency of 1 kilohertz and output voltage should be 6 volt peak to peak. And there is some additional spec, like if you can match, that can be great, but if you don't, that's also okay. Like we also want output impedance of 50 ohms. This is not straightforward, but you have to think. But this is not a must part, it's just like an optional thing. You can do it or skip it. And there is another type of amplifier which is called Wien bridge oscillator. So it goes by the same general principle as RC phase shift oscillator. However, the amplifying element does not create an additional phase shift. Like last time we used the inverting amplifier, so that's why you had like 180 degree and you had to shift it before 180 degrees so that it makes 360 degrees. So here the feedback elements should create phase shift of 360 degrees. So if you just break it down, it's something like this. You have the amplifying element and feedback element, and your feedback element should create that 360 degree of phase shift. So here is the analysis, like the V in and V out, the equations are like this, and we just applied the Barkhausen criteria just like before. We want the phase shift to be equal to 0 degree, which is 360 degree anyway. So that means omega is 1 over RC, and that's the equation that defines the frequency. And we also need to figure out the magnitude. So if you apply the Barkhausen criteria, you see like you get 1/3 of your input. So naturally speaking, you just have to have something that gives you a gain of 3, so that ultimately you have net gain of 1. It just sustains. So the design is just like part 1, except that you have a different equation to take care. Like last time you had a square root of 6, but this time you don't have one, and last time you aimed for 29 times gain. This time you just have to get a gain of 3. So you just have to find the gain of the op-amp stage, and remember, use large resistance and all those common things. And here's the simulation, like what you should do, and some advice here. And here is something about the additional task. I'm not going to be talking about in detail about it, but just to mention it. There is output impedance, which is pretty important. Like if you are feeding something, you have to match it with the 50 ohm output. If you are feeding a 50 ohm output load, because when you match, you can deliver the maximum amount of power and so on. And how do you measure the output impedance? You just see the voltage applied and current drawn, and that's your Z out. And there are other way, like you can attach a load and decrease the resistance till the output voltage is half of the previous, so that you can say, okay, it's drawing the maximum power and it's matched with the other part of the circuit when you have the half of the voltage. So that's the open loop voltage gain of a function of frequency. With different frequencies you have this is from the datasheet of op-amp 741 from the TI. So that's how they deal with it. So this is an optional part. So thank you.